Alright everybody, the next topic that we want to talk about is optimization, which is just another way of saying problems involving maximums or minimums. Okay, so the main idea is that we're going to take advantage of kind of the process that we did with related rates. So what we'll see is that these problems are kind of similar. So we'll follow a similar kind of procedure to get to our answers. So the idea with these is that we have some constraining relation and we'd like to maximize or minimize some quantity. So for example, what we'd like to do is maybe maximize or minimize an area subject to a fixed perimeter. So an illustration. So what is the maximum product that you could come up with for two numbers that sum up to 13? Well, the first way that we might approach this is let's just go and make a table of values and go and see what happens. So for example, we could start with minus 1 and 14. They sum up to 13, we get a product of minus 14. If we take 0 and 13, we get a product of 0. We keep going until we get up to 6 and 7. We see that we get a product of 42. And that works great so long as we're working with integers. So then we might wonder, well, what can we do if we aren't just considering integers? So we have to consider rationals or just floating point numbers in general. Well, the approach that we're going to do is we're going to say, well, the thing we want to minimize is this function f of two variables, x and y, which is just going to be the product x times y. We also know that x plus y equals 13, so what we could do is rewrite this constraining equation as y equals 13 minus x and substitute that expression into our original expression. So we can take y equals 13 minus x and put that in for y in the x times y equation. And in doing that, we reduce f down to just a function in one variable, and then we can deal with that as normal. So doing that, we wind up with f as 13x minus x squared. And now what we just need to do is find our critical points. Well, when we take our derivative, we see that we get 13 minus 2x, and that's only going to have one critical point at 6.5. The next step that we do is one that usually gets forgotten when it comes around to tests and occasionally homeworks. And what that is we need to verify that what we found is actually what we want. So in this case, we want to find a maximum, and we need to verify that we've actually found a maximum using one of our derivative tests. For these, it's usually easier to go ahead and use the second derivative test, because then it just means find one more derivative and evaluate at the point in question. If you use the first derivative test, you could do that to verify things, but it's generally just easier to use the second derivative test, which is what I'm going to use throughout. So, we find our second derivative is minus 2, and when we evaluate the second derivative at our critical point, we get something that is negative, and from our second derivative test that we were looking at before, whenever we get a critical point evaluated at the second derivative and that value is negative, that tells us we have a local maximum. If we evaluate our critical point at the second derivative and come up with a positive value, that would tell us we have a local minimum. So we get exactly what we'd like. We'd like the second derivative evaluated at 6.5 to be negative. It is, so that tells us we've found a maximum. So it tells us the maximum product for x times y, subject to x plus y equals 13, is going to occur when x and y are the same thing, namely 6.5. And there, the maximum product you're going to get is 42.25. Okay, so in general, what we're going to do is we're going to use a very nice setup, very similar to what we did with related rates. So some of the steps are the exact same. So the first ones are the exact same. First, read the problem, make sure that you know what you're trying to find and what you have to play with. 2, make a sketch if need be. 3, define any symbols that aren't given. Fourth, we have some quantity q that we would like to maximize or maybe minimize, so we'd like to express this quantity q in terms of the variables that we have to play with. So for what we just did, we said we have a quantity q, which is going to be a maximum product, and it's just the product of the variables in question. Let's see. So then the next one is we're going to use any of the constraining equations that were given to go and eliminate all but one variable. So in the introductory example, we had one constraining equation, we had two variables, and we used the one constraining equation to knock out one of the two variables to get us down to a function in just one variable, which we can take care of as regular. Okay, so after you eliminate all but one variable, take whatever is left, take the derivative of that expression with respect to the one variable remaining, find the critical points, and then use that to find the maximum or minimum, and then just make sure that you verify whatever you found with typically the second derivative test, but as I said, the first one can also be used if need be. And then lastly, as before, just make a concluding statement. So, you know, it's generally polite and good form to, whenever you're asked a question, to actually answer that question. Okay, so let's go and work through a few more examples. So suppose that we're given this rectangular enclosure, and we're going to construct it by taking 100 meters of fencing, building it along a barn, and we need to cover off the other three sides of the enclosure with our fencing. And we'd like to go and find the largest possible area for this enclosure. So what we see here is this structure where we have a barn and three other sides, and we need to go and build fencing for those sides. So what we'll do is we'll go and label our sides a length and a width. So we have two of one side length, and third is its own side length. So we have an L, two L's, and a W. So what this tells us is that the function we would like to go and maximize here is the area of this enclosure, so the length times the width. And what we're told is that we have 100 meters of fencing to play with. We have two side lengths of L, one side length of W, so it tells us that 2L plus W has to be 100. So we could rewrite this expression as W equals 100 minus 2L, and then go and substitute that expression for W into our original expression. Doing that, we can eliminate the W variable from A and get down to A as just a function of L, which will be L times 100 minus 2L, or 100L minus 2L squared. From there, we want to find our critical point, so we take our derivative, get 100 minus 4L, which will tell us that we'll have a critical point at C equals 25. And then lastly, we just want to verify with our second derivative, so we get that our second derivative is always going to be minus 4, and in particular, a double prime of 25 is going to be negative, so 25 will be a local maximum. Okay, so we have that L is going to be 25, the corresponding W value is 50, so the largest possible area that we're going to get out of this enclosure is going to be 25 times 50, or 1250 meters squared. Okay, for our next example, we have a lighthouse that's going to be located on an island 5 kilometers north from a point A on an east-west shoreline. We're going to have some cable that's going to be laid from L to a point B on the shoreline that is 10 kilometers to the east of A. Our cable is going to go through the water in a straight line from L to some point C on the shoreline, and then from that point on the shoreline over to B. We're told that the cost of putting the cable through the water is $5,000 per kilometer, and then putting the cable along the shoreline is $3,000 per kilometer. And what we'd like to see is where should we choose C to minimize the total cost, and then put a slight twist on the problem and say where should we choose C if we want to minimize the cost, but now we're going to put B only 3 kilometers away from A. So for this one, we could slide this point C anywhere between A and B, but clearly it would cost more if we put this point C to fall somewhere outside of A or fall outside of B. So what we're looking for here is going to be an absolute maximum for C going in between 0 and 10. Okay, so let's go and label a few different parts of this to go and simplify things down a bit. So what we could see here is that we're going to get a triangle getting formed with A, L, and C, where one side length will be 5, we'll call the other side x, and our hypotenuse will be square root of 25 plus x squared, and then we're going to have this other line of 10 minus x, so that'll be the distance between C and B along the shoreline. So we can slide x anywhere between 0 and 10, and we're just looking for an absolute minimum. Okay, so the cost that we want to minimize is going to be 5,000 times the length of the cable going through the water, so that'll be the hypotenuse of that triangle. So 5,000 times square root of 25 plus x squared. And then the cost of putting the wire along the shoreline, so 3,000 times 10 minus x. If we want to find a critical point, glossing over the steps of how we get to our derivative, we'd be able to simplify down to 1,000 times 5x over the square root of 25 plus x squared minus 3. And after some simplification, we'd find that we have a critical point of 15 over 4, so 3.75. From there, because we said we're looking to find an absolute minimum, we just need to go and evaluate our cost function c at the two endpoints, and then also this critical point of 15/4, and whatever the smallest value we come up with will be our absolute minimum. So we evaluate at the endpoint 0, so that would just be taking the cable directly to the shoreline, and then from A to B along the shore. And we see that the cost of that is $55,000. If we take our cable to hit the shoreline 3 3/4 kilometers away from A, and then the rest of the distance over to B, we'd see that that'll cost $50,000. And then if we just take the cable straight to B all through the water, we would see that the cost of that's going to be $55,901.70. So we'll pick our absolute minimum to be $50,000. Now we'd ask, what happens if we go and we shorten the shoreline between A and B to be 3 kilometers instead of 10? So we'll update the picture just slightly. So the only difference in here is going to be that we're going to have the distance between C and B is going to be 3 minus x instead of 10 minus x. So that'll change the cost function slightly to be 5,000 times that square root of 25 plus x squared times 3,000 times 3 minus x. What we see is that the critical points are still the same. The only difference between these two functions is that we've changed a constant a little bit, so that's not going to change any of the critical points. So we still have that critical point of 15/4, but now for the interval that we're looking at, 15/4 is going to fall outside of our interval. So there are no critical points inside of the interval between 0 and 3, so we'd evaluate at our two endpoints. For 0 and 3, we would get evaluating at the endpoint 0, so again, just taking the cable straight from C to A and then A to B, we would get $34,000, and then the cost of just taking the cable from the lighthouse to the point B is going to be about $29,154. Now for interest, if we'd forgotten to go and say that there are no actual critical points in between 0 and 3, we might just evaluate that cost function at 15/4 and get $29,000. Which seems very strange because we just said our absolute minimum is going to be at c equals 3. But if we'd taken this point of 15/4, what we'd be doing is connecting the cable from the lighthouse L to some point over past B and then coming back to B. And the way this function is set up is that if we picked an x value bigger than 3, the second part of the cost function would give us something negative. So what that would mean is we would be paying out money to lay the cable between the lighthouse and some point after B, but then we would be getting money back for the part about laying the cable between that point and B, which clearly makes no sense. But if we hadn't remembered to consider that 15/4 isn't going to be an allowable point here, we might have made that mistake. Okay, on to the third example. So the third example is we have some point P on the curve y equals x squared, and we would like to find the point that is closest to the xy pair 18, 0. Okay, so the distance between any 2 points you can find as the square root of the square of the difference in the x values plus the square of the difference of the y values. So for us, we're going to want to minimize the function d equals the square root of x minus 18 squared plus y minus 0 squared. But what we can do is we can actually cheat a little bit, and instead of looking at the square root of that, we can go and square both sides and look at just 18 minus, or x minus 18 squared plus y minus 0 squared. And in a moment we'll come back and see why this move works. So the reason why we'd want to do that is because now we're just looking at the derivative of a polynomial. If we looked at little d, we'd have to take the derivative of a square root and then do a chain rule, which is going to be a little bit harder, so we'll kind of gloss over that and ignore it. So the constraint that we're working with is we said that the point in question has to be on the curve y equals x squared, so we'll go and put y equals x squared in for y in our expression capital D. So now we get is capital D as just a function of x is going to be x minus 18 squared plus x to the 4. So we had a y squared and then we're replacing y squared with x squared, so we get x squared squared or x to the 4. Okay, so now we'd like to find some critical points, so we take our derivative, we find that we get 2 times the quantity 2x cubed plus x minus 18, and we could easily see that c equals 2 is going to give us a critical point. So we'd have 2 times 2 cubed, which is 2 times 8 or 16, plus another 2, which is 18, and then minus the 18 gives us 0, and that's going to be the only critical point. And then with the second derivative, we can see that we'll get 12x squared plus 2, so d double prime of 2 is going to be positive, which will tell us that c equals 2 is a local minimum. And we can conclude by saying that the minimum possible distance is going to be found with the point 2, 4, and that'll give us a distance from the point 18, 0 of 4 times the square root of 17. Okay, so now we'd like to come back and see why we were able to go and switch from the square root of x minus 18 squared plus y squared to just looking at x minus 18 squared plus y squared. Okay, so our distance function looks like this. And what we see is that it's minimized over here at 2 at some value that's a little bit over 16. So that's the distance function we would get with little d. Now what does squaring this do? Well, what we see is that all the values we have here are positive. So all the squaring is going to do is it's going to keep the relationship between all of the points. It's just going to go and stretch them a little bit. So we're not going to change where the smallest value is, because if you tell me that a and b are 2 positive numbers, but a is smaller than b, then you can guarantee that a squared is less than b squared. For example, 2 is less than 3. 2 squared is less than 3 squared. And that's what we're taking advantage of here. So we have this plot of D, but then when we switch over to capital D, what we see is the same, the shape is a little bit distorted just because of the stretching with the squaring, but we're not going to change where the critical point is, and that's the thing that we're looking for. So we were able to make that switch and simplify out the procedure a little. Okay, on to the next example. So with the next example, we have a rectangular flower garden that we're told has an area of 30 meters squared, and it's surrounded by a grass border of 1 meter on 2 of the sides and 2 meters of grass border on the other 2 sides. And what we'd like to see is the area of the dimensions of the garden that minimize the combined area of the garden and the borders. So with this one, it very much depends upon how we define the variables, and again, this is why defining the variables is kind of important, because if you just rush ahead and start labeling things without consideration for what they mean, you might make some error along the way. So what I'm going to do is I'm going to go and define this inner rectangle to have side lengths L and W, so that will be the length and width for the garden. So L times W will be 30, and then we're going to have this outside this outside rectangle with side lengths w plus 1 and l plus 2, so account for the borders. We could do this by saying that the outside rectangle has side lengths L and W, and then the inside rectangle has side lengths W minus 1 and L minus 2. We'll get to the same place in the end, but this will work fine. Okay, so again, we'd like to go and just define the function that we want to minimize. In this case, it'll be L plus 2 times W plus 1, so that'll be the dimensions of the outside rectangle. And then what we're told is that the inside rectangle, which has area 30, so L times W has to be 30. So rewriting this, we'll get that L equals 30 divided by W. Okay, so then we would like to go and eliminate one of the two variables from our expression A. Well, we're told that L is 30 divided by W, so we'll go and put that into our original function A. And doing that, we'll get that A now is just a function of W, is going to be 30 divided by W plus 2 times W plus 1, or expanding it, 2W plus 32 plus 30 divided by W. So we'll now go ahead and find our critical points. We'll get 2 minus 30 divided by W squared, or after getting a common denominator, we'll get 2 times the quantity W squared minus 15, all divided by W squared. Now, when wanting to find critical points, we could say that one place where we'd get a critical point is at W equals 0. The derivative's not going to be defined there, but we'll go and ignore that one because if W was 0, our length would be infinity, and for physical reasons, we'll ignore it. The other places where we'll get our derivative to be equal to 0 are going to be at plus and minus square root of 15. If we took minus the square root of 15, that would mean that our width and then also our length were negative. For physical reasons, we'll say that lengths have to all be positive. So here we will accept the positive square root of 15 for physical reasons. Again, we want to verify that we've actually found a minimum value in this case. So we get that A double prime is going to be 60 divided by W cubed. And when we evaluate our second derivative at the square root of 15, we get something positive. So that'll tell us that C equals positive square root of 15 is a local minimum. Putting that value back into our expression for the area, we'll wind up with the smallest possible area being about 47.5 square meters. Okay, so for the last example, some of the derivatives get a little bit messy, so we'll kind of gloss over those. The important part with this is setting up the problem. And as we would have seen with the related rates problems, the hard part is really setting up the problem. Once you set up the problem, everything else is more or less straightforward. You just have to remember a couple of the intricate steps along the way. So for problems like these, just remember to do your second derivative test and so on. But once you get the problem set up, everything else is very straightforward. Okay, so here we would like to find the length of the shortest ladder that can extend away from a vertical wall over a fence that is 2 meters high, located a meter away from the wall, to some point on the ground outside of the fence. So as we have here, we have this wall in which the ladder is resting up against, and it needs to pass over the top of this fence to some point on the ground. So as before, we can go and label a few things that show up. So we'll call the length of our ladder L. Our fence is sitting 1 meter away from the wall. The fence is 2 meters high. And it's going to this point X, and it's making an angle theta with the ground. But we could also go and take advantage of a few more things to go and write L. So if we do that, we could go and observe by similar triangles that this angle theta is going to show up at the point L, but it's also going to show up if we made a triangle between the top of the fence, the wall, and the ladder. So similar triangles would say the angle getting formed there is also L. Now, we'd like to go and write L in terms of, in this case, theta. So what we see here is that for the bottom part of this ladder, we know something about part of the length of L, this angle theta, and then we have this opposite side of 2 meters. So we could go and write this as the bottom part of our length of the length of our ladder. We could go and invoke the sine. So we could say that the sine of theta will be 2 over part of our length L, or the bottom part of the ladder will be 2 over the sine of theta. And then the top half of the ladder, we can go and use the cosine. So we have the adjacent side will be 1 meter. We'll get the top half of the length of the ladder will be 1 over the cosine of theta. So just following from some basic uses of sine and cosine. Okay, so what this tells us is that the length of the ladder we can write as 1 over the cosine of theta plus 2 over the sine of theta, as we just said. So we already have a function in one variable, and we'll just go ahead and minimize it. So we can go and find our derivatives pretty straightforwardly to be 2 times the cosine cubed of theta minus the sine cubed of theta, all divided by sine squared times cosine squared. And what we're going to assume is that we have some critical point, we'll say phi, in between 0 and 90 degrees, or 0 and pi over 2. Well, because we're looking at some value in between 0 and pi over 2, both sine and cosine are going to be non-zero, so that tells us that L prime is going to be defined everywhere in between 0 and pi over 2. So the only place where it's going to be 0 is whenever 2 cosine cubed of phi equals sine cubed of phi. Or equivalently, the cube of the tangent is going to be 2. Now we could go and observe that the secant squared of phi is 1 plus the tangent squared of phi. So that's just taking the sine squared plus cosine squared relation and dividing everything by cosine squared. So simplifying in that we know that the tangent has to be the cube root of 2, we could go and solve this expression for cosine and say that the cosine of our angle phi is going to have to be 1 divided by the square root of 1 plus 2 to the 2/3 power. And similarly, sine will have to be the cube root of 2, all divided by the square root of 1 plus 2 to the 2/3 power. Okay, then as I'd said, as we can see, the derivative here is kind of a mess. The second derivative is even worse. If we really, really wanted to go and find the second derivative to go and verify that we've actually found a minimum, we could do that. For the time being, we'll take my word that we've found that everything would check out if we use the second derivative test. So, we said that we have these expressions for cosine and sine of phi. If we really wanted, we could go and actually find what phi is, but we're not really concerned necessarily with what phi is, just what the cosine and the sine of phi are going to be, and conveniently we found those. So when we take these cosine and sine values and we put them back into our function L, we can go and find that L is going to be roughly 4.16. So it'll tell us that the length of the ladder that's going to fulfill these desired conditions, about 4.16 meters. Okay, so that wraps up everything that I wanted to say on this topic. I'm not sure exactly when I'll go and post the next video. What I'd like to do is have everyone just go and watch these 2 videos and then go and give me your opinions on this format. If you like this format, or you're able to work with it, I'll go and record the rest of the videos to cover out all of the other content for the rest of the term doing this format. If you don't like this format, please let me know, and we can all try and work out some kind of format that'll work for everyone. Yeah, I guess until next time then. So I guess that's everything that I need to say about this. So goodbye for now.